OSPF network. I've talked about. Yeah? Are you saying something? Multi-access OSPF networks. I have talked about it before. I will talk about it again this evening. And want to highlight some things that I talked to you about in the last class, towards the end of last class. Don't forget, when you want to convert a network to point-to-point network, especially the one that is broadcast by default, you go to the interface and you issue this command, IP OSPF network, point to point. I demonstrated that for you people. And a network that was broadcast multi-access before will be turned to point to point. And what is the advantage of this? There will be no election. Don't ever forget that. There will be no election. So anytime you network two routers together through Ethernet port, and when I say Ethernet, it could be fast Ethernet, it could be gigabit Ethernet, there will automatically be election between the two routers. One is going to be the D hub, the other one is going to be the BD hub. But that may not be what we want. We don't want election. We want that connection to be treated as point to point. So we go to the interface and say IP OSPF network point to point. Go to the other interface also and say IP OSPF network point to point. That is key when you want to make the connection between the two routers to be into point. Now, another thing I want to point out before I leave this alone is the loopback interface. If for any reason you want to advertise as broadcast multi-access, and that may not be what you want also, so you may end up you may have to go to the loopback interface and also say IP OSPF network point to point. IP OSPF network point to point. So take note of these two things that I just highlighted right now. Don't forget, I spoke about loopback in the last class. It is used to simulate a LAN, and you can decide to publish it inside OSPF, and you can decide to leave it outside of OSPF. The choice is yours. It depends on what you are trying to achieve. So that's that about that one. So let's talk about multi-access OSPF network. I have talked about it before. I'm going to talk about it again. So under OSPF network types, you have point-to-point, point-to-multi-point, broadcast multi-access, non-broadcast multi-access. But in the context of this CCNA topic here, we're going to be talking about only point-to-point and broadcast. So when do you say a network is broadcast multi-access under OSPF? By default, the moment you connect to a switch through Ethernet ports, it could be router to router directly or router to the switch. Look at all these routers are connected to the switch. All of them are connected to the switch. If we decide to put all these interfaces in OSPF, they are going to be seen as broadcast multi-access. And I explained this in the last class, because we can decide to add another router. We can decide to add another router. We can decide to add another router. So that is why it is referred to as multi-access. And why is it broadcast? If there's a broadcast from this router here, it goes to the switch replicates it and sent to everybody. That is why that is called broadcast multi-access. So it's a type of network under OSPF. And another one is point-to-point, and I also explained this. When you have a serial connection between two routers, serial connection using a serial port, that is referred to as point-to-point. Point-to-point. This is by default, and we can change any of these things by configuration. If we like, we can convert point-to-point to broadcast. If we can convert broadcast to point-to-point, but we are talking about default features. What they will give you by default primarily under OSPF. When you are running OSPF, that's what we are talking about, not when you change it. Okay, so for this broadcast multi-access network, I have explained something to you guys before. I don't know if it's in this slide again or the first chapter. If you have a scenario like this, if there is no election, if there is no DR, and there is no BDR, what is going to happen? Router 1 want to form neighbor with router 2, form neighbor with router 3, form neighbor with router 4. Router 2 form neighbor with router 1, form neighbor with router 2, form neighbor with router 3. Router 3 form neighbor with router 2, form neighbor with router 1, form neighbor with router 4. Router 4 want to form neighbor with this one, so the neighborship is going to be messy, as in going to be messed up. So when you have a scenario like this, that's why they came up with the concept of selecting a DR, which is like the president of the network, and then BDR, which is like the vice president on the network. So what is going to happen? Everybody will form neighbor with the president. If you have something to say, you tell the president. The president will tell other people on the network. But in case the president goes down, the vice president will take over. That is the operation on the broadcast multi-access network. There is always election to select DR and BDR. But on a point-to-point, there is no election. There is no election because it is a point-to-point network. You won't need to have DR or BDR because you have a direct connection between the two routers. You don't expect any other router to join that connection. So you know that there are only two of you there. So the point we are making now is that you must be in charge of who becomes the DR and who becomes the BDR. Just like similar thing we did it with spanning tree when we manipulated some things in spanning tree. For this also, we should be able to decide who becomes the DR and who becomes the BDR. Because after the election is done, the router that will become the DR may not be the one you want to become the DR. So you must be in charge. How will you manipulate that? We're going to say it. So what is a DR? I think they made a mistake here. This should be OSPF. OSPF designated router. Designated router is like the main router on the network. I've just spoke about it now. Is the president on the network. In a multi-access network, OSPF elects a DR and BDR. The DR is responsible for collecting and distributing LSA, sent and received. We have talked about LSA before, link state advertisement. And then the DR uses, take note of this, please. The DR, that is the designated router, uses the multicast IPv4 address 224.0.0.5, which is meant for all OSPF router. This is a multicast address. What is it going to be used for? If you want to send message to some DR other routers, there's a multicast address you will push it to. So you need to know the one that the DR used to send to the ones that are not DR. And you need to know the one that are not DR, they are called DR order. You used to send to the DR or BDR, the multicast address. A BDR is also elected in case the DR fails. The BDR listens passively and maintain a relationship with all the routers. If the DR stop producing LO packets, that is the precedence now, then the BDR promotes itself and assume the role of DR. So our BDR will always be on standby, waiting for the DR to go down. But if the DR does not go down, then the BDR will just be sitting down there doing nothing. Take note of that. All other routers become DR order. What is the meaning of that? Like in this scenario right now, let me give you an example. Let's assume election has taken place. This guy won the election. And this guy is the vice president, the BDR. What do you call this router? And what do you call this other router on this interface? They are called DR order. They are not DR and they are not BDR. You are not a DR, you are not BDR. What are you called? DR order. You are not a DR, you are not BDR. What are you called? You are called DR order. So all other routers become a DR order. A router that is neither, see, the DR nor the BDR. If you are not the DR and you are not the BDR, you are called DR order. You are not the DR, you are not the BDR. This is OSPF. You are called DR order. Take note of this. DR order use the multicast address 224 .0.0.6, all designated router to send OSPF packet to DR and BDR. So what I was saying, when the DR holders want to send message to DR on BDR, they use this MAC multicast address. So the DR and BDR listing on 224.0.0.6. This is a multicast address. You need to understand the difference between unicast and multicast and broadcast. Unicast is one-to-one, multicast is one to set off, and broadcast is one to all everybody. So we are just exploring the communication or the conversation or the, let me say, the mode of operation when you have a broadcast multi-access network. There will always be election to select DR and to select the BDR. There will always be election to select DR to select the BDR. Orders will become DR order. But there are some scenarios where you don't have DR order. Take for instance now, if I have a router connected to the switch and then connected to another router. These are just two routers here. And this is through Ethernet port. One of them will become DR, the other one will become BDR. So there will be no DR order in this scenario because there are only two routers. Just a minute, guys. Give me like 5 minutes. Yes, I'm back. Sorry, guys. Okay, so there will always be election on a multicast multicast broadcast multi-access network. But when you have point-to-point, there will be no. Can you hear me, please?
Yes, we
Hello?
can hear you. We
All
can
right.
hear you.
Yeah, sorry. I just needed to attend to something quickly. Okay, so now I'm going somewhere. How do you know the president or who will become the president, who becomes the vice president when they carry out election? The DR, the VDR. How do we know that? So let's check it out. In the multi-access topology shown in the figure, there are 3 routers interconnected over common Ethernet multi-access network. We see them. They're all connected on this interface. Now, because the routers are connected over a common multi-access network, OSPF has automatically elected a DR and BDR. How? Router 3 has been elected as the DR. Why did it become the DR? Look at it. Because its router ID is 3.3. Can you people hear me? Somebody say I'm muted. Is Ali in the house? Mr. Oroji, can you hear me? Okay, maybe it's from your side. So, who is going to become the DR? Any router with the highest router ID. Remember when we did OSPF in the last class, we talked about router ID, how you can set it. So based on what we have in this place, for router 1, look at its ID. Router 2, look at its ID. Router 3, look at its ID. So this router won the election because it has the highest ID. And this one became the BDR because it has the second highest ID. That is the first way of selecting the DR and the BDR. Any router with the highest router ID becomes the DR, followed by the one with the next highest router ID. It becomes the BDR. I'm going to explain something here. So in order for us to see what's going on here, we want to know the state of our router. When you say show IP OSPF interface, go to that particular interface. There are so many information you're going to get there. For instance, you can see the state of that particular router on that interface. Please take note, because you could have a router like this. The state on the router on this link is different from the state of the router on the other link. I can have this kind of connection here. I can say I want it to be point to point. On the other side, I can say I will leave it at broadcast multi-access. So look at this middle router here. Let's call it router 2. On one interface, it has a point-to-point connection with the other side. On the other interface, it has a broadcast multi-access connection. So you need to know the state of that interface. So in order for you to check the state of that interface, you say show IP OSPF interface, then the name of the interface. And it's going to show you the state of the interface. Here now, it's telling us that the state is DR order. And of course, it's going to now tell you who is the designated router and who is the backup router. So the designated router is the person with 3.3.3. The backup router is the one with 2.2.2. So who is this guy here? Look at this guy's router ID. It's not a D hub and it's not a BD hub. Show IP OSPF interface, then the name of the interface or the ID of the interface will give you the state of that interface. I just remember something now. This is my third class today. So the other day I was exhausted. People say stop taking too many classes. So this is the third class I'm taking today. And I can't help it. I have so many classes on my hands. And I'm still alive. Mr. Oroji, what do you say? What do you think? I just feel like, come on, this is my third class today and I'm not feeling exhausted. Can you people hear me? I'll continue to be around. I hope so. Thank you. So thank you. I appreciate it. So let's finish this. I will try to demonstrate this, but I don't know. I don't think we have any lab on that. Another command on another router. Okay, so let me show you something here. This is on router 1. Where is the router 1? In this topology, this is a router 1. This is a router 2. This is a router 3. Based on their own topology. All of this output is based on their own topology. So we can go to another router. This is on router 2. Issue the same command. Show IP OSPF interface gigabit 0/0/0. You can see that this one is BDR. Now, there's something I missed here. I want to show you something here. State is DR order. Priority is 1. I want to talk about this briefly or very soon. If I go to another router also, that's the next router. The next router, state is DR order. Which one is this one? Yeah. I will try to demonstrate this. Yeah, I will try. Let me see. You know, some people learn very well with them with lab, so I will try. So state on this particular router, I should be on router 2 now. Where am I? There are 3 router. Okay, this is router 2. This is router 1. This router 2. Then this is router 1 again. Okay, it's all right. I get it. So now I'm going somewhere. Don't worry, I will try. I will try to see. I'm still cracking my brain. Which topology can you? I'll try and demonstrate that. But I'm trying to show you something here. Priority is 1. What is this priority all about? Anytime you connect routers together on the Ethernet connection, that interface or those interfaces have by default priority of 1. Who is going to become the DR? Any router with a highest router ID becomes the DR. But if I want, the reason why we are considering or we are using router ID is because the priority number is the same on all the routers. If I want to read this selection, I don't need to go and tamper with the router ID. I can just increase the priority number on the interface, let's say to 10. Any router with higher priority becomes the DR. So the other, in other words, priority take precedence over router ID in the context of broadcast multi-access network. Priority take precedence. Priority take precedence in the context of broadcast multi-access network. Priority must come first. But because all the priority are the same, so we can't use priority. That's why we're going to use router ID. Okay. Verify DR and BDR adjacency. I have talked about this adjacency before. It's all about neighborship. OSPF router must form neighbor of a necessity. They must form neighbor. So in the context of broadcast multi-access network, you are going to have different types of neighbor being formed. One of which you're going to see full slash or DR order. Which command will you use to do that? Show IP OSPF neighbor. I issued that command in the last class. I'm going to also issue it today again. Show IP OSPF neighbor. One of the relationship between the neighbors, you can see full slash DR order. What does that mean? This is a DR and BDR router that is fully adjacent with a non-DR or non-BDR router. What does that mean? When a DR want to form neighbor with non-DR router, which we call DR order, you can say this. So you just have to be patient with OSPF. So many things to discuss. These two neighbors can exchange hello packets, update packets, queries, replies, and acknowledgements. So when a DR or BDR router is fully adjacent with a non-DR, with a non-DR or BDR router. I'm processing something here. Just a minute. Yeah. So let's finish it. I will demonstrate this to drive my point home. So you can have this one also, full slash DR relationship. This is when a router is fully adjacent with indicated DR neighbor. These two neighbors can exchange hello packets, update, query, reply, and acknowledgement. Sometimes you see this relationship, full slash BDR. The router is fully adjacent with indicated BDR neighbor. These two neighbors can exchange hello packets, update, query, reply, and acknowledgement. And then the last one is two-way DR order. This is when the non-DR or BDR router has a neighbor relationship with another non-DR or BDR router. These two neighbors can only exchange, these two neighbors exchange only hello packet. So what are we talking about here and now? For routers that are DR orders, this is the only relationship they can form with themselves. They will never go to the state of full. For routers that are DR orders, they will never go to the state of full. Don't forget from all this our explanation now today, we've been saying there must be DR and there must be BDR. So what's going to happen? The DR orders on the network will form neighbor with DR, and they also form neighbor with BDR. So in case DR goes down, this one takes over. But what if you have more than one DR order on the network? They also will try to form neighbor, but they will get stuck within two-way. 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 What is this two-way all about? Let me see if I can go back to the first chapter. Is this at the first chapter where we talked about yeah, it should be in chapter 1. Let me show you something in chapter 1. I hope I can find. Yeah, this one I'm looking for. Yeah, good. But then that is one video. Okay, this will be better on. When we're talking about OSPF operational states, we talk about down states, we talk about any state, we talk about two-way states. Your DR order will always get stuck at this state. They will not move to start state. They will not move to exchange state. They will not move to loading state. They will not move to full state. That is when the DR routers are forming neighbor with themselves. DR orders rather are forming neighbors with themselves. They always get stuck at two-way. Why? Because they cannot form full relationship. They have to form full relationship with the DR or BDR. You have to be patient. Today is plenty story. All right. So your DR routers, DR order will form two-way /DR order. This is non-DR or BDR router has a neighbor relationship with another non-DR or BDR router. These two neighbors can only exchange hello packet. Now listen to this statement. The normal state for an OSPF router is usually full. If a router is stuck in another state, it is an indication that there are problems in forming adjacency. If we know that you're supposed to form full/DR or full/DR order or full/BR order, but you are stuck in two-way and you are not a DR order, we know there's a problem. The only exception is for two-way DR orders router. They are supposed to get stuck in two-way. But all other routers, when they form neighbor with DR, form neighbor with BDR, they are supposed to, they are supposed to form full relationship. So in summary, everybody will form neighbor with DR, everybody will form neighbor with BDR, and they can have full relationship. But DR orders will never be able to form full relationship with themselves. And all of this, we're talking in the context of broadcast multi-access network. If it is point-to-point, we don't have problem with all of this. But as long as it's not point-to-point, there is always a problem. So look at the command here that we can use to verify. When you say show IP OSPF neighbor, for them on their router 2, so this guy here, this router 2 here, who is router 2? Router 2 is BDR from that our topology. But look at what it did with this router 3 that has 3.3.3. It formed a full relationship with that router, and that router is what is DR rather. And this particular router is also a BDR because it has do 2.2.2.2. It form a full relationship with which router again? With another router that is DR order. That one is not a DR. is not a BDR. So it's in full state. And that's what they wrote here. Router 1 with router ID 1.1.1 is in a full state. And router 1 is neither the DR nor BDR. That is why it's called DR order. Router 3, that is this one here, with router ID 3.3.3 is in a full state. And the role of router 3 is DR. That is why you have this way. So router 2 is BDR. It forms full relationship with the DR. Router 2, which is also BDR, can form full relationship with DR order. But DR order will never be able to form relationship with themselves. Let me give room for question. I've been talking for too long now on this. Am I communicating? Somebody says she wants me to demonstrate. I'll try. I'm cracking my brain on topology to use. So let's try to have a topology to drive this point home. Well, let me see if I can finish this. Okay, let's finish all this story. We have 3 more slides, and then you can try topology. Okay. Default DR and BDR election process. How do they carry out this election? The OSPF DR and BDR election is based on the following criteria in sequential order. Take note of this order. Number 1, the routers in the network elect the router with the highest interface priority as the DR. Highest interface priority as the DR. Now, the router with the second highest interface priority becomes the BDR. And the priority can be configured to any number between 0 and 25. If the interface priority is set to 0, that interface cannot be elected as DR or BDR. It can't even participate in the election. But take note here. The default priority of multi-access broadcast interface is 1. So all the routers have 1 on their interfaces. And that means we cannot use that priority number to make decision on who becomes the DR or who becomes the BDR, because all of them have the same priority number. Then we have to move to the second stage. If the interface priorities are equal, then the router with the highest router ID is elected the DR, and the router with the second highest router ID is selected as the BDR. If the interface priorities are equal, the election process takes place when the first router with an OSPF enabled interface is active on the network. If all of the routers on the network have not finished booting, it is possible that a router with a lower router ID becomes the DR. Take note of that also. If I have 2 routers now, and I configure this one first, this one can decide that it's going to be the DR because I worked on that one first. The addition of a new router does not initiate election process. That's why you need to be in charge. You need to be able to decide this is the router you want to become the DR or BDR on your network. So take note of the process. After the DR is selected, it remains the DR until one of the following events occurs. When the DR fails, the OSPF process on the DR fails or is stopped, or when the multi-access interface on the DR fails or is shut down. So what will make the DR to lose the election or to be unavailable? You can shut down that router. The router interface can go bad. The cable on that interface can go bad. Anything can happen to that router, and it can lose that status. If the DR fails, the BDR is automatically promoted to DR. This is the case even if another DR order with a higher priority or a router ID is added to the network after the initial DR and BDR election. So even if you have another router that has a higher router ID, once one has been promoted to become the president, it has become the president. However, after the BDR is promoted to DR, a new BDR election occurs, and the DR order with the highest priority or router ID is elected as the new BDR. So when we have the president dead, then the BDR, which is the vice president, is promoted to become the DR, we need another vice president. So one of the DR orders will be promoted to become the vice president. So another election will fail. Yeah, Mr. Samuel say, what if the failed DR comes back online? That's a very good question. I have never simulated that one. I have never tried it. It's not like Spanish tree. So I can't answer that question. So we can try it by configuration and see. Shut down the DR and then bring it out back later and see. But I doubt it. I doubt it if it take over. So the beauty of what we do in the IT list, if you have a question, you can simulate it. And then later on, shut it down, bring it back again. Is that clear, Mr. Samuel? Thank you. Okay, so how do we change these priority numbers if we want the routers to consider the priority and not the value, not the router ID? The IP OSPF priority command. If the interface priorities are equal on our router, the router with the highest router ID is selected the day out. Instead of relying on the router ID, it is better to control the election by setting the interface priorities. And I'm going to show you how to do that also. This also allows a router to be the DR on one network and DR order on another network. And that is funny. It's possible. What if we have something like this? Router 1, router 2, router 3. On this link, there will be D hub, there will be BD hub, there will be D hub, there will be BD hub. So the choice is yours. Do you want this router to be the D hub on one link, BDR on the other link? DR on one link, or BDR on one link, DR on the other link? The choice is yours. So if I go and set the interface priority of this place to say 10, by default, the other side is 1. That means this interface becomes, this router 1 on this surface becomes the D hub. The other one on the other interface becomes BD hub. What about this other side? If I want this router 2 to become DR on the other interface, I can say increase the priority to 10 here and leave this one at default. So this router 2 is both a D hub and also a BD hub. How? BDR on one line, on one link, DR for the other link. I hope that is clear. When you are changed to 0, you don't become DR or BDR. You don't even participate in the election. So take note. So if we decide to change the priority numbers, what happens is the router will consider the priority number when they are carrying out this election. And whoever has a higher priority number becomes the president. And look at how we change the priority number. You enter the interface. This is interface configuration mode. And you say IP OSPF priority. In this case, now they change it to 255. IP OSPF priority is changed to 255. And the hand command is like you want to quit and go and save your job. And why do you need to issue this command? Clear IP OSPF process so that you can reset or the election process between the router. The process, OSPF process, will be scattered and then everything will start all over again. So clear IP OSPF command is very important for you. So this is the command to change the priority, IP OSPF priority. Then you put the priority. Yes, somebody wrote something. Let me read. Okay, Mr. Samuel. Yeah, it's in the interface mode. It's the priority that determines the role of the router and not the router ID. It is the priority that determines it first. First. Do you understand me? First. So what if the priority number is the same? That's when we move to router ID to break the tie. Mr. Samuel, is that clear? Priority comes first. But if the priority are the same, then the router ID will be used to break the tie. Okay, let me see the topology that I have. Let's see if there's anything I can demonstrate on this. I didn't plan to demonstrate. Okay, let's just bring out two routers. In fact, let's make it 3. So on this link, let's play this thing to be 200.100.100.0/30. Then here 200.100.100.4/30. If you have problem with this, go back to your subnetting class, please. So 200.100.100.0/30. The usables there are .1 and 2. On the other side, the usables are .5 and .6. So let me enter these interfaces and just put IP addresses there. Let's call this one router 1. IP address 200.100.100.1 255.255.255.252. So on router 2, let's make this one router 2. Let's name this one router 1. Let's call this router 2. Oh, we already have router 1 on the network. Let's give this one, let's just change the name to router 4. I have router 4 already. Over 10, 11, 12. So let me change this router's name back to router 10. Or let me change it to router 10 rather. So hosts are 10. So let me go to the second one and call this one R11. Don't forget this one has 2 interfaces. G0/1 and G0/0 and G0/1. So it's using the G0/1 to connect to router 12. So I'll say IP address 200.100.100.4. Bad mass. What do you mean? Oh, .4 is the network address. 5 and 6 is that the usable. So let me go to the last router. Call this one, this router 12. And G0/1. No, shut down. So let me explain what I've done. Here, I have selected this network address. I put .1 on this interface. I put .2 on the interface from this network. On this other side, I put .5 here. I put .6 here from this network. So if you have issue with this address that I wrote on the screen here, you go back to your subnetting. Now I'm going to ping between router 10 and 11. I'm going to ping between 11 and 12. As long as I have direct connection, we are good to go. Now, don't forget, I'm supposed to have a LAN here. I'm supposed to have local area network here. I'm supposed to have local area network here. It just doesn't really matter. I just wanted to demonstrate this DR and BDR stuff to you guys. So, as it is right now, the routers that are directly connected can only talk to themselves. What if you want to put OSPF? Just like I told you in the last class, I can decide to go to this router here and put OSPF on the interface. Interface G0/0. We said there's another way to put OSPF. IP OSPF, maybe 10, area 0. IP OSPF 10, area 0. What's going to happen? Any IP address on that interface will be put in a OSPF 10. It's more or less like you are saying router OSPF 10. That is the same thing you are doing here now. Router OSPF 10. But this is an interface configuration mode command. So I hit enter here. I go to the second router on the same G0/0 where it's forming connected to the neighbor. Put the same command. IP OSPF 10, area 0. I'll go to the other interface, which is G0/. Yeah, I'm on G0/1 now. Sorry, I'll go to interface. Let me exit. G0/0. Put the same command. So I put it on two interfaces now. One on G0/1, the other one on G0/0. And you'll see what will happen between them now. Then I'll go to the last router and do the same thing. Now, this is a way of configuring, another way of configuring your OSPF. So let's see what has happened between these routers. They are supposed to have formed neighbor by now. Did I activate the interfaces? Show IP interface brief. Yep, interfaces are up. Can they ping? Ping 200, 100.100.2. You can ping the other side. Okay. Show IP OSPF neighbor. They are from neighbor. So somebody is already forming a neighbor. So this, in fact, let me reverse back. On router 10, show IP OSPF. Let's see some information about this. The routing process is OSPF 10 with the router ID of 200.100.100.1. That's the only IP address on that interface. It's the only IP address. So now is this guy a DR or a BTR on this interface? Because we have only one interface working here. Show IP interface brief. We have only one interface working here connected to another interface on the other side. So when I issue show IP OSPF neighbor, see what it's telling me. It has formed a full neighbor with a DR. So who is this DR? The person with 200.200.100.5. Let's go and check what we have on the other side. On this router, that's router 11 now. If I say show IP OSPF neighbor, you see that this one has two neighbors. One is 200.100.100.1. The other neighbor is 200.100.100.2. It has formed a full neighbor or neighborship adjacency with a BDR, which is the other neighbor. And also 200.100.100.6 is also a BDR. So what does that mean? My router 11 is the DR for both sides. Let's find out. Let me show IP OSPF. I'm looking for one command I'm not seeing. Show IP OSPF what's. Let me check interface. This should help me out. Yeah, wow. So now you can see on this interface 0/1, my router is what? It's a designated router on that interface. And who is the backup designated router? The guy on the other side. I have two interfaces again. On G0/0, this router is a designated router. The guy on the other side is backup designated router. So what is this mean? What this means is this. This my router is DR on this interface. This guy is BDR. Is DR on this interface. This guy here is BDR. So this guy becomes DR for here, DR for here. But we can change it if we want. So how did this guy become DR on both sides? Two things could happen. Because he came up first, or because the router ID is higher. If you compare the router ID between this guy and the others, the router ID is definitely going to be higher than the others. So let's confirm. What is this guy's router ID? On G0/1. His router ID, look at his router ID. This guy is 200.100.100.100.5. But the one that became the designated router is 200.100.100.6. How come you won this election on that link? Because he came up first. Am I communicating, guys? Can you please talk to me? On this interface, you came up first. That's why you became the D-Hub. Based on the things we discussed, if you come up first, you become the D-Hub. So we can scatter this thing and say, okay, we don't want this thing to be like this. We can decide to say, okay, we want router 12 to be the D-Hub on that link. So what do? We'll go to that interface on router 12 G0/1 and do what? Change the priority. Let me show you the default priority. Show IP OSPF interface. The priority by default is 1. Where are you? Priority is 1. Maybe I didn't use the right command for this. Okay, look at it here. Can you see it here? The priority is 1. And this guy's state is BDR. We can say, no, we want to read this selection. We don't want you to be BDR. We want you to be the D-Hub. What do? We go to that interface and say IP OSPF priority. If we say 10, 10 is higher than the default. So let's check if it's going to take it. You see that we have changed the priority of this particular router on this interface to 10. But this girl is still BDR. So we can force re-election by saying clear IP OSPF process. Clear IP OSPF process. It will reset all the OSPF processes. It will ask you, do you want to reset all the OSPF process? I can say yes. So what's going to happen? It will scatter everything and start it all over again. So we'll now see what is going to happen here now. What did you see this guy has become? This guy has become what? The D-Hub. If we go to router 11 right now, on that interface, router 11, on that interface, look at what this guy will become. On G0/1, router 11 has become BDR. Why? Its priority is 1. The other guy is 10. So you can use the priority to influence who becomes the D-Hub, who becomes the BD-Hub. The higher priority take precedence, but you must clear the IP OSPF process if you want that one to be effected. If you don't do that, whoever has become the president becomes the president. You change the priority and you restart the OSPF processes. Mrs. David, do you understand this demonstration? You ask your demonstration. Mrs. David, are you with me? Okay. So are you guys flowing with me? Yeah. Talk to me. Okay. You're flowing with me. Indicate, please. I know it's a long story today. I don't like story either. But sometimes we have plenty stories. There's nothing we can do about it. So the priority takes precedence over the router ID. The priority takes precedence over the router ID. And don't forget the DR and BDR issue is all about the interface. But let me do something here. Let me do something here. Let me do something. What if I say, guys, I don't want election on this section? No DR, no BDR. What can we do? We go to this interface and say IP OSPF point to point. We go to this interface and say IP OSPF point to point. And you will see that there will be no election. Let's go to this router first and see the type of interface that we have in that place. That interface, look at it here. It's a broadcast. That is 0/, sorry, that's 0/0. I'm talking of 0/1 now. It's a broadcast multi-access network. Under network type, you can see network type here. I can say I don't want this. On G0/1, I want point to point. I don't want election. Just a minute. So I can go to G0/1 on router 11 and router 12. Interface G0/1. Watch out. IP OSPF points. No priority. Points. What's that command here? IP OSPF network, I think. Point to point. Yes. IP OSPF network. Point to point. IP OSPF network. Point to point. I will hit enter. Then I'll go to the other side also on router 12 G0/1. IP OSPF network point to point. What did we do here? On that link, on that segment, we do not want election. We don't want election here. And you're going to see that this network type will be point to point, and you're not going to see DR or BDR. So most of the time when we have a scenario like this, we don't want election anyway. We go to all the interfaces and say IP OSPF network point to point, IP OSPF network point to point, everywhere IP OSPF network point to point. And that is what we do. So let's confirm what we just did here. So I go to this router on G0/1. Don't forget that. Show IP OSPF interface G0/1. Show IP OSPF interface G0/1. What did you see here? The network type is point to point. The network type is point to point. I can go to router 12 also and say show IP OSPF interface G0/1. You see again on router 12, the network type is point to point. You are not going to see DR or BDR in this place. There's nothing like that. Nothing like DR, nothing like BDR. And this is the preferred method when you are dealing with routers that are directly connected. You don't need any election. You just turn them to point to point. Mrs. Davis didn't answer me. I asked, are you okay with this demonstration? You told me to demonstrate. It's like she has logged out. All right, guys, are you flowing? Can I continue? All right, thank you. Okay, so don't forget when you change the priority, clear the IPOSPF process. And when you do that, the router will be forced to do another election. That is that about broadcast multi-access network. You decide who becomes the DR, who becomes the BDR. Okay, any question on that? Can I proceed to the next page? I don't know whether it's the last page. I don't think so. All right, we did OSPF in the last class, version 2. We did configuration of OSPF, and I sent lab to you guys on the video. So you should try and do those labs. All right. There are some things we can modify under OSPF, single area OSPF precisely. For instance, we can modify what is called cost. We can modify cost. Yes. we can modify cost formula. Let me put it that way. We can modify cost formula. Why did I say we can modify cost formula? You are going to see something here. Cisco OSPF cost metric. Routing protocol use a metric to determine the best part of a packet according to the network. OSPF use cost as metric, and a lower cost indicates a better part, and this cost is based on bandwidth. The Cisco cost of an interface is inversely proportional to the bandwidth of the interface. People that don't like mathematics, you will not like this, but it's not serious calculation. Therefore, a higher bandwidth indicates a lower cost. The formula used to calculate OSPF cost is look at the formula in this place. Reference bandwidth divided by interface bandwidth. And our default reference bandwidth is 10 raised to the power 8, which is 100 million. 100 million is like 100 meg. So this is the challenge here. Let me tell you this. When they came out with OSPF, the formula can only take care of 100 meg speed, 100 meg in a bandwidth. It can only work with 100 meg of bandwidth. So what happens today? In the days of gig, 1 gig, 10 gig speed, or 10 gig connection, that they was not factored in. And the reason why some of these people design things like this back then was like, we would never get to a level where we'll be in need of 1 gig. 100 meg is more than enough for everybody. So what they are trying to tell us is we can change this formula later on our router. And if you want to change the formula, the only thing we need to change is to change the auto cost reference bandwidth. When you go to your router and you see auto cost reference bandwidth, the default is 10 raised to the power 8. You can move it to 10 raised to the power 10. I think you can move it on just to take care of any new speed you have on your network. And this must be the same on all the router. But if you know that all the speed you have altogether on your router, on your network, is around within 100 meg, you don't need to do anything. OSPF will do its job automatically. It will use this formula to calculate its cost, which is 100 meg or 100 million rather, divided by the bandwidth that you have. That is how OSPF calculates its cost. But if your speed is higher than 100 meg, you have to intervene manually. If you don't intervene manually, OSPF router will calculate rubbish for you. It will just mess up the whole cost for you. Because the speed of 1 gig, I think they have a table here. Yeah, good. If you don't change the reference bandwidth, look at what is going to happen. This is the default one, which is, did I say 10 million? Yeah, it's 10 million now. No, it's supposed to be 100 million. Just a minute, let me check. 10 raised to the power 8 is what? 1, 2, 3, 4, 5, 6, 7, 8. This is 100 million. This is 100 million. Yes, it's supposed to be 100 million now. So, yeah, I'm correct. So the default bandwidth is supposed to be, this is the default bandwidth here. But look at how OSPF we deal with the 10 meg speed. It will give a cost of 1. 100 meg speed, it will give, sorry, this is the default reference bandwidth here. 100 million, 100 million, 100 million, 100 million. So now this is called a reference bandwidth. So if your bandwidth is 10 meg, OSPF will calculate, will give you a cost of 1. If your bandwidth is a speed of 100 meg, OSPF will still give you a cost of 1. Why? Because of the formula that it's using. If your speed is 1 gig, OSPF will give you a cost of 0.1, which is also 1. If your speed is 10 meg, OSPF will still give you a cost of 0.01 and also give you a cost of 1. Even though the speed is different, you have higher speed because of the reference bandwidth, which is 100 meg, which is, so it was made to take care of 100 Mbps alone back then. It will mess up 1 gig for you. It will mess up 10 gig for you. So what are they trying to tell you here? You can change the reference bandwidth inside OSPF. If you have a speed that is higher than 100 meg, you can go higher. So that OSPF will give you accurate calculation. How do you change the reference bandwidth? Where is that command there? Okay, I think okay, see the command here. How do you say change the reference bandwidth? You can say auto cost reference bandwidth. Auto cost reference bandwidth. If you put 1000, that means you want to take care of 1000 meg. That is 1 gig. If you know your speed is up to 10 gig, you put 10,000. Auto cost reference bandwidth. You do this on all your router. This command here is to take care of a speed of 1 gig and above. Or let me say I'm below rather. 1 gig and below. Yeah, it's better. That's the correct way. And this one is to take care of a speed of 10 gig and below. So you go to all your routers and put auto cost reference bandwidth command and change it based on what you have there. So what is going to happen? You can imagine if we change the reference bandwidth to 10, this is 10, 1, 2, 3, that is billion now, 10 billion now. For a speed of 10 meg, it will calculate 1000 cost for us. For a speed of 100 Mbps, it will calculate 100 as a cost for us. For a speed of 1 gig, it will give us a cost of 10. And for a speed of 10 gigabits per second, it will give us a cost of 10. So once you know that your speed on your network is more than 100 Mbps, you got to adjust the reference bandwidth on your routers. You don't do that, the router will give you, it will mess up all the costs for you. But if you don't want to tamper with the reference bandwidth, you can just go manually on all your interfaces and adjust the cost yourself. You just say IPUSF cost, you put the cost. Because I told you under spanning tree, you can manipulate the switch, the cost of the switch to the root bridge. And this take precedent above the manual, the automatic calculation that the device will do for you. But the best way is for you to put auto cost reference bandwidth on all your routers so that OSPF can do correct calculation for us. That's one of the things you can manipulate in OSPF. You adjust the reference bandwidth to take care of higher speed. You don't do that, the cost that will be calculated will be messed up. And this is a good example here now. We have a gigabit connection. And they have changed the cost to what? 10,000. And I told you 10,000 is to handle what now? Is to handle a speed of 1 gig. Is that a speed of 1 gig? Where is that in? Sorry, 10,000 is to handle a speed of 10 gig rather. So if you put 10,000, like in this case now we have 10,000, that will give us 10 billion now. The default is 100 million. 100 million, 10 million. I think it's 10 million. The default is 100 million, sorry, not 10 million. So if you increase it to 1,000, that will take care of 1 gig speed. If you increase it to 10,000, that will take care of 10 gig speed. So the default is 100 million. When you increase it to 1,000, it takes care of 1 gig. Increase it to 10,000, it takes care of 10 gig. So what we are simply saying now, like in this scenario right now, they change the reference bandwidth to 10,000. This should take care of 10 gig for us. And look at the way it's doing calculation. Here it has a cost of 10, a cost of 10, a cost of 10. Why will you have a cost of 10 everywhere? Because these are the same speed everywhere. And if you go back to our table here, you are going to see the same thing. A gig, that is 1 gig. 1 gig network will have a cost of 10. If we change our reference bandwidth to 10,000, 10,000, that would be 10 billion. I mean, yes, 10 billion. That is 10 gigabit per second. Sorry, that's 10 gigabit per second. It's still 10 billion now, gigabit per second. So there are scenarios where you have to change the reference bandwidth once you see that your speed is higher. But if you don't want to go that direction, you can just go to all the interfaces, define the cost as 10, the interface, the cost as 10, cost of 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 1, cost of 1. With this cost command, you can even manipulate the way the router makes their decision. And that will override that calculation. It will override that formula. Take note of that. For instance, now, if my router is load balancing and I want it to fail over, I can decide to say, okay, if you go through this link, it's a cost of 50. So this router will see that if I'm going through this router, I want to go to the internet, it's a cost of 10. If I'm going through the link, this link is a cost of 50. I'll use this one as a backup connection and open this one as a primary connection. And ideally, that may not be the truth, but I use a command to manipulate the decision of my router. You need to be aware of that. So different commands to see different things. If you say show IP route and then you include the route, you can see the route. How we learn about the route is through OSPF. This is the network of the place we are going to. This is the subnet mask. And don't forget, we talk about administrative distance. This is for OSPF. And this is the cost or the metric to get to the destination. And this is based on the bandwidth, the formula that OSPF has calculated for us. Correct. This is the administrative distance, and this is the cost to the destination. And if you want to manually set the cost, look at the command on the interface. You go to the interface and you say IP OSPF cost, then you put the cost. IP OSPF cost, you put the cost. And this, I told you, you can have a failover. How do you have a failover? You increase the cost of some other link. Even though the calculation probably will give you the same, you can say, no, you want one to fail over. Because you understand the way OSPF behaves, you quickly move the other side to be higher. And once OSPF sees that the cost of one link is higher than the other, it will use that one as a backup connection. And that becomes your backup route. That is that on that one. I think this should be the last part. We've talked about hello packet before. Hello packets are used between routers to form neighbor. But sometimes we want to change the timer, and that is called hello packet interval. We'll talk about passive interface in the other class, where we don't want you to send out any updates or hello packet on that interface because there is no router on that interface. You need to know when to take care of all of these things. So let's move. Is this clear first? Let me be sure we are clear with this. My long story here. The main lab we have done in the last class. It just remaining part here are just story. And one more thing is left, and that will be called as a lab. Are we good, guys? Ali, are you with me, Mr. Roger? All right, so let's move on. So sometimes you want to test, thank you guys. You want to change the hello interval between the routers and the dead interval. What is the meaning of that? So I'll just summarize this part. For the two routers to talk to themselves, to send hello, the hello time is 10 seconds. Hello timer, we call it. And the dead timer is 40 seconds. It simply means every 10 seconds, router A must communicate with router B. Are you still there? This one too must talk. Are you still there? Every 10 seconds. If router B or router A does not hear from any of themselves, for 40 seconds, they declare their neighbor dead. These 10 seconds may not be enough for you. You may want to change it. The 40 seconds may not change as in increases. You may want to reduce it. Why would you want to reduce it? You probably may not want to wait for 10 seconds before the network or before the router will know that one neighbor is done. You want it to probably happen faster. So you can decide to reduce your hello timer to 5 seconds or hello interval to 5 seconds, and it must be multiplied by 4. The dead interval must be multiplied by 4. So you increase the dead timer to, that should be 20 seconds. So you are simply saying, if I don't hear from you after 5 seconds, sorry, I should hear from you after 5 seconds. If I don't hear from you after 20 seconds, I believe you are dead. You are no longer available as my neighbor. That is the way the routers operate. But of course, on the interfaces that do not connect to any other router, you have declared those interfaces as passive. Hello packet should not be going out of those interfaces. So how do you change this? You can see the hello timer here is 10 seconds. The dead timer is 40 seconds between OSPF routers. Actually, it depends on the network. This is between point-to-point network, on point-to-point network. On broadcast, the timer is different. So for two routers that are on a point-to-point network, the hello timer is 10 seconds. The dead timer is 40 seconds. It simply means I don't hear from you within this period. I believe you are no longer available. And this is between interfaces of the two routers. What do I mean by that? Let's say this is router 1, router 2, router 3. Between these two routers here, my hello interval and dead interval can be different. Different in the same time. This one can use the same thing. And on the other side, it can be different. But whatever router 1 on this interface is talking to router 2, their hello interval and data interval must be the same. The hello interval and dead interval between router 2 and router 3 must be the same. They can be different. If one side is hello interval is, let's say, 5, the hello interval on the other side is, let's say, 10, they are not going to form neighbor. The hello interval and the dead interval must be the same between the two routers. So what else do you see from the output of show IP OSPF neighbor? You can see how long I'm going to declare you dead if I don't hear from you. Dead time. For the next 35 seconds, that means I'm expecting to hear from you. That is with this neighbor. And the other neighbor in the next 31 seconds. I don't hear from you, I declare you dead. How do we change this timer? You go to the interface and you say IP OSPF hello interval. You put the interval. It's always in second. IP OSPF dead interval. You put the dead interval. It's always in second. And you can decide to remove the one that you put so that they can go back to the default. So if I put, let's say 20 here or 5 here, this one will be 20 because this is multiplied by 4. Dead interval is multiplied by 4 of hello interval. So you may want to reduce it so that you can have a faster convergence. And they don't advise you to reduce it. They tell you not to reduce it. We have done something that is even smaller than seconds. We did milliseconds and it worked perfectly. So look at the command here. IP OSPF hello interval 5, IP OSPF dead interval 20. What does that mean? I expect you to send hello packet to me every 5 seconds. And if I don't hear from you after 20 seconds, I believe you are no longer available as my neighbor. And so if you use show IP OSPF neighbor command, you'll see the dead timer here. This guy is waiting for the next 37 seconds to declare the neighbor dead. If the neighbor doesn't send hello packets within that 37 seconds, the neighbor is declared dead. Take note of this. This is the last part. And that's the most important one for us in this class today. Any question before we proceed? I want to demonstrate this one, but I think my battery is running out. Not my laptop battery, human battery. I will just explain the concept to you guys. Let's go back to my topology. Look at the topology we worked with in the last class. We connected New York router to London router. Thank you, Mr. Diagbo. I was feeling like a Superman when I started the class. But now it's like the energy is draining. Now, what we did in the last class, we didn't have any internet connection. We didn't have any internet connection. Don't forget we ran OSPF on the network here. What if you want to inject internet connection into this network here? We have two ways of doing that. London router can have its own ISP in London to serve these local area networks. New York router can have its own ISP to serve this local area network. This is what is obtainable in most organizations or nowadays. But before, this is what they normally do. Look at what they used to do. They will tell the headquarters to get internet connection down from service provider. When the internet connection comes down into the service provider, they will now use OSPF to distribute it to all other branches. OSPF within the OSPF will now distribute it to all other branches. That is what people normally do back then. But this will create a single point of failure for you. Because if anything should happen to New York router or the ISP in New York, London people are down, other branches are down, they will not have internet connection. So if this is what you want to achieve, you want to inject internet connection from the headquarters to all the branches through OSPF. That is what this remaining part, the remaining part of this class is all about. Remember, the routers can talk to themselves. Information, but this is what we want to do right now. It's a different ball game. We want to inject OSPF into this. I mean, want to inject internet connection into this route. That is what default route propagation is all about. Yeah, we have done something like this before. I was thinking we have not done something like this. So let me explain one more thing before I go back there. When we did static route, I taught you guys, we configured default route on a router that is connected to the internet. I think I taught you guys something like that. If you remember, I say on this router, we're going to say IP route 0.0.0.0.0, 0.0.0.0.0, then the next up IP address, which is the router for the service provider. Did you remember that? Did you people remember that when we did default route under static route in CCNA2? Good. I remember telling you guys that when you use default route is when your router is connected to the service provider, because you don't know all the networks on the internet. So you just want to tell the router any network you don't know about, and you don't with any subnet man, just send it to the service provider. The service provider knows what to do. This is where we're going to also learn something else or add something to our knowledge. This New York router is one connected to the internet. On this side, it will be using default route. On the other side, it's using OSPF. OSPF to talk to the routers within its own organization. It could be 50 routers, 100 routers, 150, 200, depending on the numbers of branches. But this New York router also has a leg to the service provider. So what happens if London router want to go out? As long as London router doesn't have default route to go to the internet, it won't. Nobody here will be able to browse the internet. If there's another router here, this other router here also needs its own default route. If there's another router here, that router also needs its own default route. So for every router on our network or in our organization to access the internet connection, they must have default route. But we only have one router that has a connection to the service provider. So all of us can make use of that router to go to the internet. But how do we get this default route? We can inject that default route inside of OSPF, so that when New York router is talking to London about OSPF, it will also tell that router, guy, in case you have a message for anybody outside of your network and you don't know where to send it to, just send it to me. That is what default propagation is all about. I can help you to reach the internet. So it will communicate to you about local area networks, and it will also tell you that in case you need to go to the internet and you don't know how to go to the internet, send it to me. That is what we want to talk about here. So let's go through the slide, then we'll come back and we'll just do brief demonstration on that. Default route propagation. We have only one exit to the internet, and there are other local area networks connected to that organization in other cities or other country. And we just want to use just one location to access the internet. That's what we're trying to do here. So we want to propagate a default static route in OSPF. We want to propagate a default static route in OSPF. So what is the static route all about? To propagate a default route, the edge router must be configured with the following. The default route must be available in that router that is connected to the service provider. So in this our topology now, I'm going to add another router and call that router ISP. I'm going to connect it to this our router that we have already on the network. I'll call this one ISP, and I will configure the default route and point to that router there. We are coming to that. So now look at this command. The default information originate router configuration command. This instructs how to be the source of default route information and propagate the default static route in OSPF. So look at another example here. In this scenario right now, they have configured the default route and pointed it to this loopback. I can even make use of loopback to do that. I think I will just use that one. And then they now go inside OSPF and say default information originates. Default information originate. What does that mean? Router 2. Tell other routers on the network if they need to go to a network they don't have an idea about, they should send it to me. So you see that this default route we have configured is going to be sent to other routers on the network. Let's do it and see. Let's use loopback to demonstrate that. Before we start the journey, let's go to this router and check their routing table, see what we got in their routing table. Show IP route. Look at what I got. No static route in my routing table. How do you know a static route? You see it like this. Candidate default with asterisk. Let's go to the other router here in New York. Show IP route. No static route. But I want to create one imaginary static route. And I want to create imaginary service provider. What is going to be my imaginary service provider? My loopback interface. Let's say interface loopback 0 or 1. IP address, let's say 200.100.100.1, 255.255.255.255. I've explained this before in one of the classes. No shorts. I don't really need that. Then in this router, I will now say IP route 0.0.0.0, 0.0.0.0, 200.100.100.1. Let me, it's that won't work. Let me say .2. What am I doing here? Let me check their own example. Maybe I have to bring my router back. Okay, I see the way they did their own. They use the loopback interface itself. I think I will use their own example. Where am I? Should be it now. Okay, my New York router. So let me yank off that thing. Let me remove this and put it back. But I want to use the loopback 1 that I did now. Loopback 1. Let me see if it works. Without route, default route without gateway, if not a point-to-point may impact performance. I know. But did you accept it? Let me find out. Show IP route. Beautiful. This guy has taken my default route. Look at my default route now. Oh, Mr. Samuel is saying, why is my subnet mask 255.255.255? I have mentioned that in the class. When you are indicating a network of one host, meaning we don't care about the network address where you came from. We don't care about your broadcast address. We just want to relate to that IP address. We use 4255. We're just concerned about that address. We're not talking about any class now, because there are 4 octets in that address. So please factor in first octet, second octet, third octet, fourth octet of the IP address. If you just put an IP address without the subnet mask, the router won't take it. You must put a subnet mask. Exactly. You can't put any IP address without subnet mask. See what we got here. S simply means it's a static route. Asterisk means it's a default static route. Or let me say S and asterisk simply means it's a default static route. Default static route, and it is going through this. So we have created, can you please mute yourself? It's a default static route. Now I need you to see something again. Default gateway of last results. Simply what? I have a default route on this router. For any network, for any network, or let me say for any subnet mask with any network, this router knows where to go to. Where will it send it to? It will send it to loopback 1. Who's on loopback 1? My service provider, my imaginary service provider. But if we go to London router does not have that in its routing table. It does not have default route. But it has OSPF communication, show IP, OSPF enable. It talks to the other guy. They are friends. You can talk to New York router. So what I'm going to tell New York now is this. Please tell London router about this default route. So what will I do? Show IP protocol. Let's see what we configured in OSPF there. We've configured router OSPF 100. We go back inside that place and say router OSPF 100 default information originate. We're simply telling New York router that default route you know about. Whenever you are talking to your friends using OSPF neighbor and you are talking to them about networks that have been advertised, also tell them about the default route. Tell them that if they need to go to the internet, they should send the message to you. If I hit enter now and go to London router, you will see that London router also will have a default route in its routing table. Show IP routes. You see now, London router has a default route in its routing table. Now you can see it is home asterisk. It's a default route that was gotten through OSPF. It's a default route that was gotten through OSPF. It wasn't configured manually on London router. It was gotten through OSPF. And E2 simply means external route type 2. These are beyond the scope of this class. We have E1, we have E2. External route type 2. It's coming from outside. So if London router needs to go to the internet, it knows that it can send the message to 192.168.103.2, which is New York router. And because New York router has access to the internet, it's going to help everybody under London to go to the internet. So even if you have 200 routers on your network, all you need to do is to tell the main router that is connected to the internet, just say default information originate under OSPF. Make sure you configure the default route and go to OSPF there and say default information originate, and it will move the messages to all that default route to all other routers on your network. And what we did with that message all the way leads to the router that is connected to the service provider. They say follow who no road. Now it's only New York router that can go to the service provider. That's why you see it like that. So two things. On the router that is connected to the service provider, we call it edge router. That's our New York now. Edge router. Configure the default route and go to under OSPF and say default information originate. It will move this default route to other routers on the network. And that will be it. Exactly. Is that clear? Mr. Samuel, are you with me? Ali, are you there? Is it clear, please? Yeah, Mr. Samuel, is it clear? All right, guys. Today's class is plenty story. But we are done with the story. So that is how you inject default route into OSPF environment. You go to the router that is connected to the service provider, and then you configure your default route on that router, and you tell that router to send the message to other routers. So that's all. So other commands you need to learn is show IP OSPF enable, show IP OSPF protocol, IP protocol, show IP OSPF, and show IP OSPF interfaces. And I've used all of these commands in the class before. So that is gonna be it. Any question? So how do you get to cement this knowledge? Lab, 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 lab. Don't ever forget that. Lab, 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 lab. Ali, I need you to help me do something. The non